Welcome to Autonomous Vehicles on the Roads of the Future. This project aims to assess the efficacy of evolutionary techniques when applied to autonomous vehicles on modern roadways. We approach this problem via three sub-projects as follows. My sub-project is investigating the viability of evolved controllers for use in shared space. This project makes use of NEAT to evolve the controllers, with the aim of investigating the efficacy of evolved controllers for use in intersections that use the shared space architecture, in comparison to that of heuristic controllers. In addition, we also investigate the ability of the evolved controllers to generalize across different intersection designs and compare that to the ability of evolved controllers on standard road designs. Here we can see some footage of a heuristic controller, a controller evolved on shared space, and a controller evolved on traditional intersection designs when applied to a modified pedestrian priority square with high pedestrian density. Overall, the results of the experiments indicate that the controllers evolved on shared space both generalize well across all tracks assessed and significantly outperform heuristic controllers and the controller evolved on traditional intersections across the majority of shared space intersection designs, and otherwise perform similarly to both other controller types on typical intersection designs. The primary concerns that demonstrated by the evolved controllers involve observable strange behavior such as weaving back and forth or stopping for no apparent reason, and that the controllers can have rather high variance at times.
I will now be presenting my part of the project, Novelty-Driven Evolution of Vehicle Controllers. The aim of this project is to use three different evolutionary techniques: objective-based, novelty-based, and hybrid-based, which is a combination of the first two, to create separate vehicle controllers that can then be compared to determine the performance of each technique and which one is the best. Now, to show this, I've got examples of three controllers being run on the same intersection. The first one is the objective trained controller. We can see that vehicles, when they detect that something's in front of it, they stop for a period before going forwards. Now, in contrast, the novelty controller, it pauses when it sees something in front of it, but it keeps moving forward. This makes it more efficient in getting through across the intersection, but it can lead to more collisions. And we can see in the hybrid approach that it combines the two previous options of it stops, but it doesn't stop for very long, which means that it is safer than the novelty, but is also more efficient than objective. Though overall, one method hasn't completely won out over the others, and results overall show that they are more comparable to each other and that hybrid sits between novelty and objective in terms of performance.
My sub-project is on the coevolution of vehicle controller intersection pairs. Coevolution is a technique in which multiple evolutionary algorithms are run in parallel, such that an expanded search space can be used, in which a single evolutionary algorithm may not be suitable. Two different techniques were used for the generation of vehicle controllers, NEAT and CoSyNE. These were then compared to a generalized controller in which the intersection did not evolve. The generalized controller was evolved using only NEAT. The overall aim of this project is to create controller intersection pairs such that a different controller is active in each intersection. As can be shown here, the generalized system struggles in the more complex intersections, and even in the simpler intersection, is outperformed by the basic CoSyNE approach. The specialized NEAT system doesn't perform as well as the CoSyNE system in the more complex intersection, but in the simpler intersection, far outperforms it.